Hey everyone, I am Ansh Rastogi and today I'm going to present my topic image resizing using different convolutional techniques. Let's look into it. Okay, so what resizing basically means? Resizing is nothing but the amplification or de-amplification of a signal, and the signal we are concerned today is an image. So what's basically an image is? Image is a two-dimensional array of some numbers where each number represents a color, or we also call it as a pixel. So a set of so many pixels arranged in a 2D fashion collectively forms an image. Okay, so let's look into the resizing part. Resizing includes both upsampling and downsampling. The downsampling is nothing but we have original image of let's say n cross n and we want to downsample it to n by 2 cross n by 2. So for this we can simply drop out every second pixel in the image and downsample it easily. But the trickier part comes in upsampling. In upsampling, we have to increase the number of pixels, and there is, I guess, no way to get information out of nowhere and get the pixel values in between. Let's say here we are given with an image of 3 cross 3, and we want to upsample it by a factor of 2, which makes it to be 6 cross 6. Yeah. So we have arranged the original pixel values accordingly, but there are a lot of new introduced pixels which are meant to be filled. Since we cannot generate entirely correct data out of nowhere, so interpolation is the only thing we are left with. Interpolation is nothing but the estimation of a new pixel value or a new value based upon the correct or the given values to us. So, talking about these methods, we are going to talk about a total of four methods to interpolate the values in between the original ones, right? So, let's start. Nearest neighbor interpolation. It is a very naive way of interpolation, first of all. In this method, what happens is for every unknown pixel, it just simply copies its value from its nearest known neighbor and just place itself at the position, right? As you can see in this illustration, we have upsampled a 3 cross 3 image to 6 cross 6. These pixels have just simply copied their neighbor pixel values, right? Overall, the image looks fine, but the image have a very blocky appearance, or there will be surely a loss of smoothness and a loss of detail for sure. Right? Let's look into the code of this. Here is the basic implementation of nearest neighbor interpolation. Uh, what happens here is, let's say we are given with a pixel map of an interpolated image, and we are known with the value it is 10 here, and we want to interpolate its neighboring values, right? Its coordinate will be 0 comma 0, it will be 0 comma 1, it will be 1 comma 0, and it will be 1 comma 1. Okay, so both x and y will get round off to its nearest neighbor, right? So this 0 will get divided by 2 and gets rounded off to be 0. This one will get divided by 2 and get rounded off as 0. So this coordinate will simply copy the value at 0 comma 0 itself. So this will become 10. Same for 1 comma 0, this 1 will become 0, this 0 will become 0, and this will also copy 10. This 1 comma 1 will also round it off to be 0 comma 0, and 10 will be copied here itself, right? So using these, every unknown value is gets interpolated and the process is being done. Let's look at the here is the result for nearest neighbor interpolation. Here we have used the original image of 600 for 600 and we have upsampled it by a factor of 2, and similarly we have downsampled it by a factor of 2 on itself. We will compare all these at the last bit also for different methods. Let's look into the next method. It is bilinear interpolation. In this method, what happens is instead of just simply copying the known pixel values, it takes a weighted average of the neighboring pixels, right? So this can solve the problem of smoothness, right? So the in between two known pixel values, there will be a smooth linear decrease or increment of colors, right? So let's look into the code of itself, right? Here is the basic implementation of bilinear interpolation. Let's look into this schematic diagram first. Here we are given with two known pixel values, that is 233 and 200. Uh, its coordinate are 0, 0 and 0, 1, and we are required to interpolate a value at 0, 0.3. This 0 0.3 suggests that there are a total of 10 pixels that are meant to be interpolated. So we are only talking about this only. In since the name is linear interpolation, what happens here is the interpolated value depends upon how close and how far it is from its neighboring atoms, its neighboring pixels basically. Since it is a very since it is quite close from this, so this pixel value will have a higher weight in compared to this. Ultimately, the sum of these two will constitute this pixel value that is 223.5 here. Let's move ahead. This is the result for bilinear interpolations. Here we have used the same image that is 600 cross 600 image and upscaled it by a factor of 2 and downscaled it by a factor of 2. So we will compare all the results at the end. Let's look into our next interpolation, that is bicubic spline interpolation. In this method, what happens is between every two known pixels, there are a set of interpolated pixels, right? So those interpolated pixels are not arranged in a linear fashion. Instead, they are arranged in a polynomial fashion, which eventually makes the image a lot more smoother and a lot more clearer as well, right? Okay, let's look into the here is the basic implementation of bicubic spline interpolation. What happens here is uh, every pixel value is simply a weighted sum of its surrounding pixel values, right? So here we are using a factor of 3, which means every pixel is, affected by its neighboring 9 pixels, right? So weight of each pixel will get decided by the cubic polynomial, the standard cubic polynomials that we have defined here itself. So using this, the in between pixel values are gets calculated. Let's look at the results. So these are the results for bicubic interpolation. The image we have the same image is being used, that is 600 cross 600, and it is get oversampled by a vector of it. Let's move to, before moving to the next section, let us look at the comparison of linear and cubic interpolation. Here we are given with the known pixel values. So this blue curve is just for the visuals. We are only given with these red points, right? And we want to interpolate a value in between them. Let's say I want to interpolate a value at this. So we will use its neighboring pixels and interpolate it respectively. Okay, so for linear interpolation, we simply know that linear interpolation only use its nearest neighbors. So its nearest neighbors are these and these only. So rest of these will not affect the interpolated value at here, right? So for linear interpolation, it will basically a linear weighted sum of these two neighboring atoms only. So visually, you can visualize it like it will simply stretch out a linear line between these two pixel values and interpolate it respectively. Let's say for this pixel, it will simply stretch a linear line, and we want to interpolate a value here. So the interpolated value will be this, right? But the actual value is here, this, but the interpolated value using linear interpolation will be here itself, right? Okay, so here we can look at the actual curve also. Uh, each two pixel value is get connected with a linear line, and all the new interpolated values can be, used or interpolated with these lines itself. The ground value is this at this point. The ground value is this, but using the linear interpolation, we've interpolated value as this. So this difference you can call it as error, right? Since we cannot find the ground truth value all the times, we are just interpolating it using its neighboring atoms, neighboring pixels. Let's look at the cubic interpolation. Here you can see in cubic interpolation, the curve is a lot more smoother. Instead of linear lines, it gets connected with a cubic curve. In linear interpolation between these two points, it will simply plot out a linear line, right? So let's say we are talking about this pixel. So its interpolated value for linear will be this, and its interpolated value for cubic interpolation will be this, and the truth value will be this. So you can clearly see that the error for cubic that the cubic interpolated value is far more closer to the truth value from the linear one, right? So we can here it is tremendously visible that cubic interpolation is far more better than the linear interpolation, right? Further, it is a lot more smoother than linear itself. Okay. Convolution interpolation. Here what happens is, let's say we are given with our original pixel points that is showing is as blue curve, right? So we will use a uh, kernel you can say, or a set of pixels, and we will traverse it over the image and generate a uh, interpolated curve and get the interpolated values in between the true values. Here you can say we have used a triangular kernel, and it simply gets convoluted over the original curve or the original image. And here the interpolated curve is quite linear since the kernel is not very good. It is quite similar to the linear interpolation as well. So simply changing this kernel can, can lead to quite more better fitting than a linear one, right? So you changing this kernel can be a very good move. Using this, we are moving to our next interpolation method, that is Lanczos interpolation. Lanczos interpolation is simply a convolution interpolation, but its kernel is quite good. So the kernel here we are using is called Lanczos kernel, or Lanczos kernel is simply this mathematical expression, and its graph looks like this. The benefit of using this because is you can say it is a lot more since it is a lot more curvy or smooth. It generates a very smoothly interpolated curve, which pretty much you know interpolated a very good rate. So let's look about Langlos convolution. As we have looked earlier, this blue curve is the original data point that we are given with, and this purple is the Langlos kernel. And when we convolute it over all the images, we will get a far more better, smooth, interpolated curve that we are getting here than from the kernel we have used earlier. It is triangular kernel, right? It is far more better than the triangular kernel. You can agree with me on that, right? Okay, so it is the curve for it's not cubic spline, it is length loss first of all. So it is the result for length loss interpolation. Okay, so we have discussed all four methods, and now is the time to check on the performance metrics and compare the results for all. Okay, so here are the performance metrics for all the methods. These are the enlarged images. These are the crop cut out of enlarged images, and these are the shrunk images that we have generated using those MATLAB codes. Here you can clearly see that the quality or the sharpness or the smoothness, you can say, is very much increasing in this order, right? As we have discussed, nearest neighbor is not interpolating very well. It is a very like the output curve is very pixelated or not very smooth. But using better interpolation techniques, using better curve fitting techniques, we can get to like we can minimize a lot of error. Right. So these are the shrunk images and these are the enlarged images. You can see Langlos and bicubic spline methods are fairly good in comparison to these nearest neighbor and wide area interpolations. There will be always a scope of improvement, right? Uh, Earlier, what we are doing is we are simply interpolating the values using the neighboring pixels itself. We are not taking the value from some nowhere, right? But using some advanced techniques like generative networks or deep learning, what we can do, we can have a set of resources. We can have a large data set of images, and we can have some features extracted from it, right? So when we want to resize an image, instead of just using its neighboring pixels for interpolation, it will also use that the bunch of images that we have used for its training to accurately or precisely guess its interpolated value, right? let's say we want to resize an image of a car, there will be surely a bunch of images of car that will be present in the data set, right? So it will predict. So simply, it has a lot more data just other than those neighboring pixels. So it will interpret far more better, right? Talking about hardware-based approaches. Hardware-based approaches is simply integrated with the camera itself. As soon as you click the capture button in the camera, what happens is instead of taking a single photo, it will take a bunch of photos with a slight vibrations in each photos, right? So here, where will we there will be a set of data or a lot of data for the image to get resized. So let's say if you click the photo and want to resize then the image. So while resizing, you will have a bunch of images wherever you can find out the pixel values, right? So let's say you want to resize your image from 100 cross 100 to 200 cross 200. The missing pixel values will surely be in the slight, like due to the slight movement, those pixel values will be get caught. So you can simply take out those pixel values and can generate the image well. Further, using some advanced techniques like super resolution and using some high-end networks, you can interpolate and resize the images very well. Okay, so that's my time, guys. Thanks you very much for attending the session.